Now let's look at our last problem today. This problem says we have a hot water pipe. The radius is given. The temperature is also given. This is the outer surface temperature. And then later it describes it has a thick insulation wrap around it. So everything we are interested is outside this R1. So whatever inside this R1, the hot water, we don't really care in this problem. And also here, the outer radius is also given as R2 and also the surface temperature T2. So we are interested in simply the conduction through this insulating layer, and heat of course transfers out since it's a hot water and you're trying to insulate it from like you're fighting against the heat dissipation, right? So the heat goes out. The conduction heat goes out. The problem then asks, what's the temperature distribution within this insulation layer? It asks us to plot the temperature against the radius, right? Then since we know the heat is going out, then it must go down. But how exactly it goes down? Does it go down linearly or curving downward, curving upward? Then we can do an analysis like this. So we can recall what happens if by the way, this is clearly a steady state 1D steady state 1D problem, right? So in a steady state 1D slab, a plane wall, a slab, or a Cartesian coordinate system, we have two surface temperature as T1 and T2. What does the temperature distribution look like? This case is linear, right? Why is this linear? Linear means the temperature gradient is a constant. And remember, how did we get this gradient is constant? We did something like this. So maybe we can also draw a control volume in this case. Maybe we draw this control volume from this surface to a arbitrary surface. We just call it X. We call this place 0. This is L. Just we put the control volume, the boundary of the control volume at a arbitrary location X. Means this result is true for any X between 0 and L, right? Then however much the heat comes in from here will go out from this boundary. Then this Q conduction is a constant. This is a constant. This equals to, according to the Fourier law, a homogeneous material K is a constant, and area we just said is plane wall is a slab, so this area is also independent of x, is also a constant. Then we have everything constant, then this guy must be a constant. However, in the cylindrical coordinate, things start to change. So here I will only draw one sector of the cylinder. I can draw this way because of the symmetry, right? It's isotropic, so I can take any sector at any angle around this cylinder, I will get the same result, right? If I draw the control volume now from this R1, the R1 surface to a arbitrary surface at, we just call it R, between R1 and R2. Again, due to the symmetry, there's no heat transfer in this surface, right? Like if it goes in one direction, then it breaks the symmetry, things don't work out, right? There's no heat transfer through this and this surface. Then whatever energy comes in will go out through this surface. And then we call the Fourier law. This is again a constant. Homogeneous material K is also constant. But when we look at this area, things start to change, right? So before going to the numbers, we notice this area increases with R. So when R increases, this area increases. But the other two terms are constant. Then dt dr must decrease. Oh, sorry. The absolute value of this thing must decrease, right? Because here the constant can be positive, can be negative. The absolute value of this thing must decrease. Then if we go back here, with R increase, the absolute value of the gradient decrease means the slope of the temperature distribution is not as steep, right? It's shallower, it's not as steep as a smaller R, which is what we are drawing here. So at a larger R, the slope is shallow. At a smaller R, the slope is steep. Then this case is correct. It curves downward. And here, since we have the chance, why don't we also quantify this one? We know how to calculate the area of a cylinder, right? This area equal to 2 pi RL. And this L, again, this L, we can see that as a unit 1, or just put the actual L, it doesn't matter. Point is, we have a constant equals to area. This area is another constant times R. Try it again. Right. I simply expanded this area, and everything here is a constant. Then we are at rdtdr is a constant, then dtdr is a constant over r, and that's our ODE course, right? This t must have a distribution of log, right? With two constants. And we can plug in this pair of known values of r and t, plug in these two into this general solution, and get C1 and C2. Right? So then not only do we know this temperature distribution, in this case, is bending downward, we also know this is actually a log curve.